All right, let's resume our discussion. Today we are going to continue the discussion on the Markov chains. It's chapter 7, and these are the 4 items we are going to talk about today. We are going to start with the classification of states, which could be a bit dry, and then we are going to move to one example, one application that's called the Gamble Ruin, and then we are going to talk about stationary distribution. At the end, if we have time, then we are going to talk about the random walks. Right. So recall that what is a Markov chain? Markov chain is really just that in a lot of cases you can visualize the Markov chain as there's a set of states and there's a transition matrix, right? Sometimes you can draw the transition matrix by using a directed graph, right? So for instance, you do have in this particular Markov chain we have 5 states, right? So that we can draw a transition matrix that has 5 rows and 5 columns. Right. So you can really just think that we are performing a random walks on this graph according to the transition matrix. Let's say that we are starting at the state B, and there are 3 possible ways to go out of state B, and basically there's 3 possible ways that you can specify that as PBA, and then PBD, which is here, and PBC, right? So maybe like let's say this is 1/2, this is 1/3, and then it's 1/6, right? So now it's correspondingly you really have the the Markov chain can be expressed in this way. B to A is 1/2, B to B is 0, B to C is 1/6. B to D1 is 1/3, and the rest of them is 0, right? So you can really just state the Markov chain in either one of these 2 forms. One would be the graph form, the other one would be the matrix form. Right? So in mathematically, sorry for that, it's really just that the probability if my Markov chain. What is the probability of the Markov chain in a particular state, given that I know that the Markov chain was previously is in a different state, right? So this is specified by this so-called transition matrix, right? Right. And now we can talk about a bit about the classification of the states, right? So this is where we are here, right? So classification of states. And let's start with one definition. It's a bit dry, right? So definition 7.2 is we call that state J is accessible from state I if for there exists an integer n such that Pij n greater than 0, right? If I is accessible to from J, and then J is also accessible from I, then we say that I and J commute, right? So this is I and J commute, right? They communicate. Sorry, that communicate. So intuitively, that's a pretty straightforward statement, right? So when we say that the exists at n such that Pijn is greater than 0. What is let's recall what's the definition of this one? Pijn is really just the probability that st plus n equal to j condition on st equal to I, right? So basically that's that after n step, what's the probability that I hit j when I start with I, right? So this statement basically says that there exists a path in the graph, in this kind of graph representation, such that the path length is going to be n, and then the second condition is that and if I look at the starting point here, it's I, the start at I, and then end at j, right? And if I look at all the transition probability, all this number here really has to be all greater than 0, right? So everything here has to be greater than 0, right? If such path exists, that basically says that there's the probability that I can move from I to j using n step is going to be greater than 0, right? So this is really just saying the existence of such paths, right? It's a combinatorial property if we look at that look at the graph representation, right? So that basically, if we just even translate that into the more straightforward terms, it's really just that the it's that it's I and j are connected in the graph the terminology, right? So we can really move from I to j, right? Well, because this is a directed graph, right? So it's really just that j is reachable from I, right? But if both condition happens, right? So if I can move from I to j, and find a way to move from I to j, and find a way to move from j to I, then we say these two nodes are communicate. Right? So now we can also next thing we want to define is the so-called equivalent class. Right, so I think this is also something you saw in the discrete math, right? So in the graph terminology, is really just a strongly connected component. We will see the connection is actually very obvious. So let's say that what would be the equivalent class, right? So basically that we say that the i's node and the j's node are within the same equivalent class, within the same equivalent class if there are three conditions. The first condition is that it's reflexive. That means that for any state I in this whole class, let's say this is whole equivalent class, then if for any I in this class, then I commutes to I, right? What do I mean by I commutes I? That means that if I start with a node I in this graph, I start working out, eventually I will be able to find a way back home, right? So there at least exists some way to be back home. Like we will discuss about this issue a bit later, right? But it's also possible that we can always be back home, but the expected time to be back home is going to be infinite, right? So this is reflexive. And the second one would be the symmetric. Symmetric basically means that if I and j are in this equivalent class, right? So then the I and j communicate, right? So that means that there's a path that's connected between I and j, and there's also a path that connects between j and I, right? So here, like, I think I was not clear, right? So this is the definition of the equivalent class, right? So it's really just a subset of nodes, right? So it's not definition on the pair of the states. It's definition on a subset on states, right? And the third one would be transitive. Sorry that I'm not able to pronounce this very well, right? So that basically means that if I and j are communicating to each other, j and k communicating to each other, then that implies I and k communicating to each other, right? So that's pretty straightforward too, right? So if there are two classes, right? So if I already know that I can move from I to j, right? To j it's movable, and from j to k it's also movable, right? It's obviously that there really just implies I can move from I to k by just trying to move I to j and then j to k, right? So sorry, maybe I didn't express that clearly, right? So let me repeat, right? So in case in this graph we sort of already knows that I and j are sort of the communicate, then that really just, and we also know that j and k communicate. That really implies that I and k can also communicate. Why? Because like there exists a path that's moving from I to k. This is really just I can move from I to j and j to k, right? So this is obvious, right? So both are really just given conditions, right? And there's also exists a path that's moving from k to I. Right? Why? It's I can definitely move from k to j and then j to I, right? So that's really just the third condition, right? So if these three conditions are all met, then for a subset of nodes here, then we say that subset of nodes here forms an equivalent class, or right. So now basically the equivalent class, and the strongly connected components are really just closely related the components, right? So in the sense that if I look at this graph, right? So so look at this directed graph, right? So let's recall what is a strongly connected component. If one component here, right? So U, that's a subset of vertices, such that like for any nodes UV in U, right? There's a path that's connecting, that's moving from U to V. Then we call this component, this whole component as the strongly connected component, right? So we can sort of see that for any strongly connected component, that also forms an equivalent class, because if you check all these three conditions, it really just holds. Right. So it's not really this kind of definition is not really that useful. Like I didn't remember what was the last time I saw this guy. Like I really need to be careful with this definition, but it's really something that you need to keep that in mind. There's such kind of things, and then in case that you don't really you really, in case someday you need to see the detailed definition, you sort of need to know that where do you find those definitions, right? And so actually the equivalent class and strongly connected component that's actually set as a lemma here, lemma 7.4, right? And also, by the way, like this part, like it's pretty dry, right? I'm not sure I'm really presenting that in a very good way, right? So I do encourage you to read the textbook on your own to make sure that you actually also understand the concepts. To double check that, right? So now let's move to the next definition, right? So this is the definition of 7.3, a Markov chain is irreducible if all states belong to one communicating class. Right? So okay, like this is another concept that I think like you also need to just make sure that you understand that, right? So an equivalent class it's actually a definition that's in the logics, and when we say there's an equivalent class of a subset of nodes in the Markov chains, we call this equivalent class the communicating class. Right? So these are really two the same thing, right? So basically this definition says that it's defined what is reducible. So if you really just don't look at all these terms here, the communicating class, equivalent class, because either you forgot or you never learned that, it's really just that it's irreducible if and only if the graph is strongly connected. Right. So this is actually the only thing you need to know. Right. So that's the definition 4.3, and then we move to we also mentioned the lemma 4.7 so that's the definition of 7.3, and then we also move to the lemma 7.4, right? The equivalent class and strongly connected component, right? So they are really talking about the same thing. And the next thing we need to talk about is the recurrent. So before we proceed, let's really talk about what we have covered just now, right? So there's a concept called accessible, right? There's also concept called the communicate, right? Those are really just on a pair, right? Then we talk about the third thing would be the communicating class, right? So that's really just the equivalent class. Equivalent class, right, in the defined in the logic sense, right? And then the fourth one would be the irreducible. Right, so the irreducible is really just means that it's the whole there's only one single communicating class, or just in the graph, or in other words, it's really just that the whole thing is strongly connected, right? The fifth concept is recurrent. So it's really just that you sort of like we are listing out a lot of concepts which I personally don't feel that's terribly useful in practice, but again that you need to be aware of the existence of this concept, right? So and let me talk about that, right? So the definition of force 7.4, right? A state is recurrent if Ri sum of t greater than equal to 1, Rii t is 1, and is transient if sum of t greater than equal to 1, Rii t less than 1. Right. So now like that, now we also need to define this RIIT, this term here. This is really just the probability of ST equal to J, and for I less than equal to 1 less than equal to S less than equal to T minus 1, as T doesn't equal to J, and condition on ST equal to I. Right. This is Rij. Let me just rewrite everything. Sorry about that. Rij t equal to probability of st equal to I, and for any s between 1 minus t minus 1, st doesn't equal to j, and condition on I start with s0 equal to I. Right. So what does that mean? That means that like just let's parse this equation here, right? That means that I start with the state I, and I traverse for t steps, right? So there are t steps here, right? At the end, I need to reach j, and before I reach j, I need to make sure that within the first t minus step, I never reach j, right? So that really just literally translates to that probability that this walk hits J for the first time at T. Right. So what's the probability that at time T, this random walk hit J for the first time? Right. So this is the definition of Rij of T. And now, if we have this definition, then we can look at what do we mean by recurrent? Then recurrent means that like I sum up of everything, right? So let me just write down this again. T greater than equal to 1, Rii t equal to 1, right? So what does that mean? When t equal to 1, that means that what's this probability that I return to i's node at one step. Right. So this is really just that the let me just change a different color. This is Rii0, right? So if I can also look at the let me move to here. What is Rii1? Rii1 means that within one step. Actually, this is Rii1 because I did this start with 1. And what is Rii2? That means that within 2 steps, right? So that's I go back to I, right? So this is a probability return to I at exactly at this time t second step, exactly at the second step. And similarly, like we can also talk about Rii3, right? So Rii3, right? So that's this within 3 steps I return to I, right? So if I sum up this one, it's really just that the probability that I will eventually return to the state to my original state, right? So now if I use the picture to show that, right? So I start with a very giant Markov chain. I focus on particular node, right? I let the random walk to work on the Markov chain, right? So if I sum up everything here, t greater than or equal to 1, Rii that's really just that. What's the probability I eventually hit back this Markov chain, right? So let me give you some examples, right? So before I give some example, right? So let me just wrap up the definition here, right? So if this is 1, that really just means that I eventually I will hit back to the original node, the node I start with. If this is less than 1, that means that there's a certain probability I will never return. Right. So let me give you some example, right? So some very simple examples. The first example is that like if I just really draw this graph, right? So A, B, C, right? So it's A to B with a third probability, A to C with a third probability. It's everything is a third, right? So basically, if you draw things in this way, it's a third, a third, a third, a third, a third, a third, and so on and so forth, right? So there's something that's coming back at that's a third, right? So if I use this Markov chain, I know that if I start from here, I take a random walk, like no matter what how the random walk is going to evolve, like with probability 1, I'm going to always to be able to hit back A, right? So this is obviously the case where A is the so-called the recurrent. And let's also give you an example that's some simple example that we will never return to a particular state, right? So let's say that my Markov chain really looks like that, right? So it's with probability 1 A move to B, with probability 1 B move to TC, and so on and so forth. And in this case, when, for instance, if I start with A, I will just directly go from left to right without ever being able to come back to A, right? So this would be just the definition of the transient. Right? But this state is going to be interesting, right? I start with here, I always hit back. That's really just a very trivial definition of this is a recurrent. So now we do have this definition of the recurrent and the transient. Then we also need another definition. It's the so-called expected time to return. Right. So this is defined as HII. Right, so this is defined as HII, right? So and then if we use the definition of expectations, right, it's really just sum of probability, sum of t greater than 1, t times RII t, right? So this would be the probability I spend exactly t steps to go back to state t, and then this would be just because like it's computing the expected time, like we need to scale that by t. So of course, like this is undefined for transient state. So that is like if I is transient, right, then basically so what I call the RII infinite, right? So basically this is the probability never return. Right. This is going to be, let me just erase that and be a bit more careful, right? So this is going to be greater than 0, right? So if I sum up everything here, right? So if I sum up things here, let me do this one, t greater than equal to 1, t times RII t, right? So roughly speaking, there will be the term that's really just positive infinite times RII t, right? So there's infinite, right? There's always a chance that I never return. In this case, the return time will be infinite, and that's the reason that the expected return time remains undefined, like in case that the state is transient. Right. So now let's look at another definition, right? So now let's move to here, right? So we start with like accessible, moving to communicating class, and then moving to do irreducible, and finally we were at the recurrent, right? So we are going to do the sixth one. It's the positive recurrent. So just like I figure that maybe it's really just helpful to list out everything so that you know where we are heading. It's a lot of it's really just a collection of a lot of pretty straightforward definitions, right? So let's start with the positive recurrent, right? Definition. Now we are at the 7.5, right? So a recurrent state I is positive recurrent if HII is not infinite. Otherwise, it is non-recurrent. So let's really just repeat what is this definition saying, right? So if I know that if I start with the Markov chain, I look at one specific state, I know that it's with probability 1, I will eventually return to I, probability 1, and I will eventually return to I. Then the question is that under this situation, what's the expected time to return? Right. So one would probably just think that, well, because with probability 1 I'm going to eventually return, then it seems that the expected time to return is always a finite number. And this definition at least hints that maybe that's not true. It could exist a situation that expected time to return is infinite. We will eventually return, but the expected time it takes to wait until we return is going to be infinite, right? In this case, it's called non-recurrent. Only if the return time is finite, we call this state positive recurrent. Right? So now one question that we are curious to see is that what would be non-recurrent state looks like. So now the textbook actually gives you an example, right? So basically the example here is that we state we have a lot of states: the state 1, state 2, state 4, 3, 4, 5, and then actually all the way down to n. So, and actually it's all the way down to infinite, right? So we do have infinite amount of states, right? So now let's draw the transition matrix, right? So every time, right? So when I move from one state to the next one, right? The probability, it's with high probability that it's always moving to the right, right? So let's set this one to be 1/2, this one to be just 3/1, 2/3, and this one to be 3/4, and so on and so forth, and 4/5. Right? And there's also a small probability that we are returning. This is 1/2, this is 1/3, and this is 1/4, and so on and so forth. So now let's for the nth state is 1/n, right? So you can just do that, so on and so forth, right? So now let's start with computing the probability that we never return. Right? So let's stick to this state, right? Let's really just focus on the state 1, and then we want to compute the probability that we never return, right? This probability is calculated as product of j equal to 1 to t, j divided by j plus 1, right? So that basically means that we have to like keep going to the left before, like, so that we make sure that we never return, right? So this is 1/t. Right, so this is an obvious calculation, right? So this actually goes to 0 if t goes to infinite, right? So we sort of want to this n, or sometimes it's written as t, to go to infinite, right? So that really just means that this probability is 0, and now that really just by the definition, this is going to be a recurrent state. Now we also can compute the H11. H11, let's use the definition t equal to 1 to the infinite, t times R11t. Right. So R1t is that the first time to return back to 1 at the time t. Right. That really just means that if like this probability, this event happened only if from time 1 to all the way down to t minus 1, it's moved to the right. And from time t, that it's moved left. Right. And then we can calculate the probability here. if I want to keep moving to the right, is 2 1/2 times 2 divided by 3 times 3 divided by 4, and all the way down to t minus 1 divided by t. Right? This would be the chain of the probability describing the first event. And then we also need the second event to happen, right? So this is 1 over t. Right? So if you you calculate that you simplify this this term, then you will get something like the t times t plus 1 in the denominator. Numerator is 1, right? So this is really just that these two are the same. Right? So h11, let's say this is actually this one. So now let me just rewrite this one. It's just S11 equal to t greater than equal to 1 t times 1 over t times t plus 1. Right, so these two get cancelled, and eventually we got this one, t greater than equal to 1 t plus 1. Right, so this one actually diverges. Right, this sequence diverges. Right, so that's the reason it's infinite. Right. So now we sort of like went through the actually a very giant set of definition, but so now let's move to the next one. It's the lemma for 7.5, right? It's again then not terribly useful, but we do want to be aware that this kind of results exist. So for this lemma, we actually don't provide a proof, but let's write down the statement. It's really something, again, I repeated a number of times. The materials in this region, it's really fundamental, but not that useful. So you still need to go. We still need to be able to at least be aware of this result. It's in a finite Markov chain. First one is at least one state is recurrent. And in second one is that all recurrent state are positive recurrent. Right. So this actually is this left as an exercise, right? So if you are interested in that, then you should work on this lemma on your own. Right. So now finally, let's again look into what we were doing here, right? So we have the communicating class and irreducible, recurrent, positive recurrent. The final thing is that the next thing would be the so-called periodic. A periodic. Let's define that, right? So again, it's very helpful to really just to keep track of all the definition that appears in this portion. It's painful. So definition, the 7.6, right? So a state J in a discrete time Markov chain is periodic if x6 an integer delta greater than 1, such that probability of xt plus s equal to j condition on xt equal to j has to be 0, where s is divisible by delta, right? So and then we say that a Markov chain is periodic if any state is periodic. So and also a state, we also say that a state is aperiodic if it is not periodic. Right. So now again, there are three things going on here. Right. The first one is that we define the state is periodic. What do I mean that for this giant chunk of things? That giant chunk of things is that if so say that let's really just that put up a concrete example. So let's say that this positive integer delta is 2, right? So now and then let's say that the state j here is periodic with delta equal to 2. That really just means that probability of xt plus 2 equal to j condition on xt equal to j is 0, and probability of t plus 4 equal to j, t equal to j is 0, and so on and so forth, and then plus 6, right, and then x plus 8, right, so on and so forth, right. That says that, like, if I want to return the state j, I have to take odd number of steps, right? So I can't take even number of steps to return to the same state. So let me give you an example of a periodic Markov chain, right? The periodic Markov chain is really just here, right? So here it's a bipartite. Sorry that again. Sorry, really just too many concepts. Even for myself, I get confused a little bit. This is unless, right? So let me just correct that. Unless s is divisible by delta, right? So that really actually means that this is t plus 1, t plus 3, t plus 5, t plus 7 are all 0, right? So now, so an example here would be a bipartite graph. In the bipartite graph, right? So we have this kind of graph, right? So let me just use I. Look at this node and let's call this I, right? In order for me to return to I, like I have to jump to the left and jump back to the right, right? So if my first step, if when t equal to 1, so xt equal to I, that basically means that in the even step, it's in the even steps, right? So if I look at 2, 4, 6, and 8, so our active state, the way our random walk will be at the right hand side. Right. When it's right hand side, that basically means that probability as xt cannot be I when we start with I, right? So that really means that at the second step, at the fourth step, sixth step, and eighth step, it's impossible to hit I, right? Only if in the third step, in the fifth step, in the seventh step, like in this all steps, it's possible to get back to the right hand side, the left hand side, and there's a possibility that we can hit that I, right? So this would be an example of the periodic Markov chain, right? Now, if you see that, right? So now, so that really just means that only if like within a constant amount of like every delta amount of step, there's a chance that I return to J. So otherwise, it's not possible to do that, right? So let me give you a second example, right? So in this case, delta equal to 3, right? So basically, if in this case, if I start with A, right, it's every 3 steps I return to A. But if I just only walk in using 2 steps, right, I can only reach to C, right? So this would be an example, like this is the example where it's a periodic with delta equal to 3. So now, after we define a state is periodic, we can also talk about a Markov chain. The entire Markov chain is periodic, like in case that any state is periodic. And eventually, we can also say that a state is aperiodic if it's not periodic. Right. So this definition is really just that when a Markov chain is periodic, like it's really just behave funny, and then this is usually the case we don't want to handle. And in a lot of the practical scenario, that this is indeed the truth, right? So this is really just a definition that we want to make sure that there are sometimes that things go funny, you need to be a bit careful, right? But oftentimes that this really just doesn't happen, right? So this is periodic. And eventually, we are going to talk about something called ergodic. All right, so this is the last definition really that's happening in the Markov chain. For a while, at least in section 7.2, right? So basically, the definition here is that an periodic positive recurrent state is an ergodic state, and a Markov chain is ergodic if all states are ergodic. Right. So now let's really really just that again, like this, the conceptually what we are doing here is that we start with accessible, then we can talk about communicating. After we talk about communicating, the irreducible is really just says that everyone communicates, right? So recurrent just says that like not only it's reducible, and the chance that I'm coming back is I'm coming back to the same state is going to be 1, probability 1, and this set would be the same set, or like it's really progressively talking about the same sort of things, right? Including the positive recurrent, and the periodic is actually an orthogonal concept, right? So you can have a positive recurrent positive recurrent state that's periodic, right? So now if it's positive recurrent and it's also a periodic, then it's called ergodic, right? So basically, it's really just that we are building up a set of concepts eventually that leads to a definition of our own definition that's a normal not Markov chain. When we have a normal Markov chain, where we sort of expect like every state, if we start with every state, we can eventually go back and at the same time that there's no this kind of periodic behavior happening here. Right. So next, let's move to the corollary. Corollary. Right. Any finite, irreducible, and a periodic Markov chain is an ergodic Markov chain. So now again, like this is a sort of the sufficient condition to make a Markov chain ergodic. Like you need to be irreducible. Basically, that means that the whole within the whole graph, if from a strongly kinetic component, it needs to be finite. We don't want to talk about the infinite graphs, and we also want to make sure that like it's not periodic. And if all this three condition holds, then it's what we call the ergodic chain, and then it's usually what's considered as like the normal chain. Right. So now after all this definition, let's talk about something called the Gamble-Ruyin. Gamble-Ruyin, like underneath, it's asking this question, right? So so the question is like this: I have a Markov chain, right? And the transition probability is pretty straightforward most of the time, right? So half of the probability goes to left, and half of the probability goes to right. And so on and so forth, right? So now there are only two special states here. It's the left end and left end, and the right hand. Right? So in these two special states, it never goes out again. Like once we hit the state, it will stick to the state forever. Right? So this is a Markov chain.